Okay. So, the next thing that I would like to talk about is a corollary of our principle that we have seen so far, or I would say dual, I would say. So far we have seen that if I have an input into an LPTV system, right, and we sample the output at say NTS, it does not matter whether it is NTS or NTS plus T naught, we know that you can always find an equivalent LTI system. We said that this is equivalent to you have x of t driving an equivalent LTI filter, and if you sample the output, right. In other words, if you sampling, I mean one way to kind of think of sampling is you can think of this as a delta train, delta of t minus k t minus say L T S, right, and you get some output sequence here, correct. So, what this is saying is that you will get the same output sequence if you take t minus L T S, and so these two are the same. All right. Okay. Now, the next thing is what? Well, it turns out, as we will see going forward, that the opposite is also true. So, let us say you took an input x of t and modulated it with an impulse train. So, we know this already. Okay. And let us say it drives an LPTV system at Fs. Again, please note that the rate at which the LPTV system is varying is exactly the same as the frequency of the modulating train. All right. Now, what we are going to see, and let us see what let us call this y of t. Now, the LPTV system can be represented by its as usual by its Zadeh expansion. So, you have h 0 of j 2 pi f h sub minus k of j 2 pi f So, this is e to the minus j 2 pi k f s times t h sub k of j 2 pi f and you have e to the j 2 pi k f s times t, and this is the equivalent of the system, and then it is now being driven by x of t and an impulse train delta of t minus LTS. Okay. Now, there is I mean, if you remember how we got at this result, what did we say? Well, we were sampling, and when we sampled, we were sampling the outputs of the we were sampling the sinusoids at k times Ts, and they all became 1, correct. So, so in other words, if the multiplication and sampling happen side by side, then it is easy to reduce the block diagram, right, like how we saw in the first case, right. That's how we saw this result, right. Here unfortunately, it looks like, well, the multiplication, the impulse train is here, but the multiplication is happening on the other side. So, if we want multiplication to happen on the left side, it turns out that it is pretty straightforward to do, and I am just going to draw your attention to that. So, what we have right now is, in the kth arm, is h sub k of j 2 pi f, right. This is e to the j 2 pi k f s times t, all right. Okay. And I can think of this as e to the j 2 pi k f s times t. I can multiply this by e to the minus j 2 pi k f s times t, and what should go there? What is this? Yeah. So, this should simply be h sub k of j 2 pi f, and this is e to the j 2 pi k f s times t. All right. You agree that both of them are equivalent, correct? Now, what I want to do is draw your attention to what is there inside this box. No, think carefully. So, let us say we excite this by e to the j 2 pi f t. What is there there? E to the j 2 pi f minus k f s times t. So, what is the signal there? H sub k j 2 pi times f minus k f s times e to the j 2 pi f minus k f s times t. It is an LTI system. So, basically whatever the input frequency is there, it just gets multiplied by a gain. So, what comment can we make about the output signal here? It is h sub k of j 2 pi f minus, let me just push the whole thing this side. H sub k minus k f s times e to the j 2 pi f t. All right. So, what conclusion? If you put in e to the j 2 pi f t, the output is this. Does that depend on time? No. The gain imparted to a sinusoid at f, right, by the red box does not depend on time. So, is it and the output is at the same frequency as the input. So, is it time invariant or time variant? It's an LTI system. And what is the equivalent transfer function of the LTI system?
H sub k j 2 pi.
Yeah, it's simply h sub k of j 2 pi times f minus kfs. And what all that this is doing, I mean, intuitively this h sub k of f minus kfs means that the response of that is moved from from DC to is centered at k times, it moves towards the right around kfs. And why does that make sense? Let us see what the box is doing. It is taking an input frequency, right, pushing it to a right, yeah, it is moving it to e to the minus kfs, that is going through the filter, and then it is getting pushed back again, right, pushed low and then pushed back up. So, so therefore, you can write, so if you basically call this f sub k of j 2 pi f, all right. So, by definition therefore, I mean instead of writing h sub k of j 2 pi f minus kfs, I am just going to call that another filter which is f sub k of j 2 pi f, okay. And therefore, I can rewrite, I can therefore using this observation, I can rewrite this block diagram or manipulate this in this way. I will first multiply by e to the j 2 pi minus j 2 pi k minus j 2 pi k f s times t this becomes, sorry, is this sorry, is plus yeah. So, this is f sub minus k of j 2 pi f, correct. This simply becomes f 0 of j 2 pi f, which is basically the same as h 0 of j 2 pi f, right. Remember the k term, that f sub whatever is just simply moving that h sub k to, yeah. Now, this becomes e to the j 2 pi times plus k f s times t, and f sub k of j 2 pi f, okay, and this is y of t. All right. Now, well, when you multiply this, so now you can see why this makes sense, right. If you now you're cascading two multipliers, right. So, multiplication by two numbers is basically you can multiply the two numbers together and you have a single multiplier. When you multiply these two together, what happens?
It's like 1.
That all becomes 1, right. So, this becomes 1, all these become 1. So, therefore, this is equivalent to taking x of t sigma over L delta of t minus LTS, correct. and what do I get here? All these become 1. So, that is simply
F equivalent.
sum over f sub k of j2 pi f, and this is y of t. Does it make sense? So, what is the moral of the story? Well, if you have x of t and you have an impulse train, and you excite it, you excite an LPTV system and you get some output, you can think of this as the output of the same impulse train exciting
Equivalent to LTS.
an equivalent LTI system and you will get the same waveform in both cases. So, F equivalent of j2 pi f is simply the sum of f sub k of j2 pi f, where f sub k of j2 pi f, the f filters are simply the harmonic transfer functions j2 pi f minus kfs. Okay. So, this is a dual of the other situation where there we multiply the output by an impulse train and look at the output signal, right. Now, it is I mean you can think of that as this is simply turning the other one input to output. Does it make sense? So, the obvious question now is, so why is this even relevant, right? And a practical example of why where this may help is so in practice, I mean whenever you want to convert from digital to analog, right. So, you have a discrete time sequence x of n exciting a DAC. The output of the DAC basically will typically do will have a staircase like wave output here. So, in the spectral domain, the staircase like output waveform. So, if x of n has a spectrum like this, right, this will have images around, and let us say this DAC is sampling at Fs. So, if you did not do anything, what you will have is you will have images at multiples of Fs. So, okay. So, what you need to do is to put in a smoothing filter correct, and the job of the smoothing filter is to remove that high frequency images, right. So, a very common example of this is whenever you are trying to modulate an RF signal, I mean a baseband signal to RF, you will convert the baseband digital signal using a DAC. The output of the DAC can't directly be modulated up, because if that happens, then all these images will also appear at RF, right, and that becomes a problem for the for your neighbor who's trying to receive a very weak signal. So, you must adequately suppress those images before you can go into a mixer or a modulator. So, that job is done by a smoothing filter. Now, this is the output of the DAC. So, here basically what you end up getting at the output is a clean spectrum like this. So, if this is B and this is minus B, at least ideally you are supposed to see no images. Of course, in practice there will be some finite rejection. Now, the output of the DAC, right, can be, so let us call this x of t, or let me call this x hat of t, right. X hat of t can be thought of as you take a sequence x of n,
multiplying with the
I mean you can yeah, and then you multiply, or rather let me see. So, you can think of it as taking a signal x of n t s delta of t minus n t s sum over n, right. Okay. This convolved with, that is the impulse sequence, and every DAC has got a pulse shape. So, this goes into a filter. Pulse shape is p of t. Typically, this p of t is a non-return to 0 pulse, right. So, this is goes from 0 to T s, okay, and this is the x hat of t, that is the output signal of the DAC. Okay. Now, this goes into a, I mean this has to go into a smoothing filter, right. This is but this sequence is a modulated sequence, correct. It is basically equivalent to what we see here. So, what this is saying, this is a corollary to what we have seen earlier, where we sample the output of an LPTV system. Now, what we have just seen is telling us that, well, there is no need to, I mean in principle, if the smoothing filter is replaced by an LPTV system, right, okay, then also there is, I mean at Fs, right. So, you can find an equivalent LPTV system whose response, I mean where these two can be the same, right. There we were trying to replace
LPTV system.
an LPTV system with an LTI system. Here we are doing the opposite, right. You can potentially use an LPTV system to smoothen the output of the DAC, right, and the hope is that because you have an LPTV system, you will be able to what do you call, you will be able to perhaps make a filter which has a much sharper roll off at high frequencies than is possible with an LTI filter. Remember, an LTI system is simply a special case of an LPTV system, right, where only that H naught is there and none of those other filters are there, right. So, there is obviously a lot more degrees of freedom here than they are in an LTI system. So, these can potentially be used to advantage.